All right. So today I want to use these 90 minutes to tell you about efficient federated learning. And of course, federated learning is by now such a hype topic that it's very difficult to make a comprehensive presentation. So what I want to do is give you a little bit of the basics and the intuition, go into what it means to be efficient in this context, and then give you at least a few hints towards or tease towards current interesting research directions. Please ask questions during the talk. That's perfectly fine. Let's keep it as open as possible. All right. Let's start with the truism that data is distributed. And we have all these data generating devices. This is true since a long time, but gets more and more true every day with mobile phones, sensors, the whole internet generating data in various places. And our previous way to deal with this was what I call centralized machine learning. So you have these devices that generate data, and then you have a communication infrastructure, and you send the data to a cloud or a cluster or some huge storage where you can then run a machine learning algorithm to train a model. Now, I call that centralized, even though in this cloud, you will probably run a high performance parallel machine learning algorithm, some version that uses all your DGX machines and all your CUDA GPUs. So it's not in general, not parallel, but we have to centralize all the data in one spot. And this is the big problem we're facing today, because what I want to argue is that centralizing all this data is infeasible to impossible. And let me give you a few reasons why. So my go-to example is that of autonomous driving. It was estimated that an autonomously driving car generates roughly 1 gigabyte of data per second. And if you want to transmit that, you have a problem, because with current mobile network 4G, you can only transmit 37 megabytes. Now, you could argue that you can compress it a little bit. You don't need all the raw data. And maybe we at one point get 5G and this is all no problem anymore. But even if you could transmit it, just imagine what it means processing so much data. If you just take the cars that Volkswagen sold in 2018, that's 10 million, and assume only those would transmit 1 gigabyte per second, that's 10 petabytes of data per second that you need to process. And just to put that into perspective, at CERN, the unrivaled champions of large data processing, they process roughly 25 gigabytes per second. So this is just not feasible. A second example is that of Siemens. They at one point released that they roughly collect 2 exabytes of data per day. And that comes from their oil platforms, from their gas turbines, wind turbines, all these sensors and all these machines. And while they manage to collect this and store this, they admit that processing is hard. There's a second big problem here. These machines are operated by customers of Siemens, like a gas turbine, right? So these sensor data, if they get into the wrong hands, like a competitor, it would reveal a lot about how this company actually runs their machines. So they don't want to share this data. At the same time, if you want to do, for example, predictive maintenance on these data files, then you need all this data, because otherwise you cannot build a good model. So you're a bit caught in between. You cannot share the data. At the same time, you need it. And sharing it reveals a lot. And I'm now working in healthcare, where the problem is even worse. There, it's not only that it reveals a bit about a competitor, you're just not allowed. I mean, they close your entire business if you would share patient data. So we are in a situation where we have huge data sets that are distributed, where communication often is a bottleneck, and where we have huge privacy concerns. And the current approach that is very favored is federated learning. So let me give you a rough intuition of how it works. There are many ways to look at it. I find this intuition always very easy. So assume you have a set of clients or learners, devices. Let's think of mobile phones. They all generate data. Usually we would send this data to a cloud. What we instead can do is run our machine learning algorithm on that device and produce a local model. Now, here are already a few assumptions. First of all, we assume that we have all data necessary for training on that device, including the labels, which is not always the case. And the second big assumption is we can actually train that model that we want to train on that device. Now, try running a modern natural language processing model on a mobile phone. That's a bit infeasible. Nonetheless, if we can do that, we end up with all these local models. And these are usually fairly bad because they've only seen very little local data. And now we have some server or a cloud or a cluster, doesn't matter. I usually call it the coordinator because it coordinates, but I think in the literature, it's usually called just the server. And you send all these models to the server. Now, first of all, that's good because you only communicate models. Often models are smaller than the data they've been trained on, so that saves communication. And you don't send actual data, which is also good because it somewhat preserves privacy. I'll talk a little bit more about this later. And now at the server, you end up with a huge bunch of very bad models. That's not very helpful. But if you can aggregate them in some way into a single, better model, then you have won. Because either you already have a model quality where you're happy with, or you can redistribute that aggregate back to your clients, continue training there with that as a starting point, and iterate this whole process until you reach a model quality that you're happy with. This, in a nutshell, is what federated learning does. And some of you that might have read into the topic will say, but there is this and this algorithm that does it a bit differently. I will talk a bit about the name federated learning later and how it relates to those. Okay. So if we assume this is what federated learning does, then it gives us two design choices for a federated learning algorithm. Well, basically three. One is which algorithm do we use at the learners? And then the two important ones that are related to the aggregation are how do we aggregate and when do we aggregate? And the way I described it is that I said it's an aggregation operator and we have a synchronization operator. Some of that didn't really stick in the community, so you might also forget it right away. Nonetheless, we need a little bit of notation. I'm not math heavy today, but there is a bit of formulas I throw in. If you have any questions, please do ask. I usually use the notation that we have M local learners or clients or devices, and we assume rounds in which we work. And in each round, a client observes a local data set. Now, this formulation is a bit ambiguous. What I mean is it could be, for example, a mini batch. So you have your whole local data and you look at, in each round, at one mini batch, or think of an epoch, something like that. And in each round, your learning algorithm runs an update. So it takes the data set, it takes your model, and it does an update step, just like a mini batch update for deep learning. And as usual, we have some input space, usually a real value vector space. We have an output space, which is either classification or regression for most cases. And we have a model space of functions. And for most federated learning algorithms, we assume that this is parameterized in such a way that we can easily aggregate models. So typically think of a linear model that you just have for each feature one weight. And each model is a set of weights. Or think of a neural network. We assume all local neural networks have the same architecture. Then they are basically represented by the same vector of weights. And each configuration then defines a model. So how do we then aggregate? The most straightforward and to my how would you say? Well, as a researcher, it's not very nice that it works so well, but the most straightforward version works incredibly well, and this is you simply average models. What does it mean? So if you again think about linear models, you have a weight for each feature, you have several of these weight vectors for each local client, and you just average them weight by weight, and that gives you the aggregate. That is fairly simple. Then you can think of your models as points in a high-dimensional space, and the average is just a point somewhere in the middle of them. And this geometric perspective is actually very helpful. You might also directly see that. Yeah, oh, yes, please.
Yes, so let's. Thank you very much. So I have a question. So does this kind of a process already assumes that the data is already integrated? Because so I'm talking about, so if you're talking about one single company trying to do federated learning, then they have devices already providing the data in the shape that they expect. But if you have like in the clinical example that you provided, you might have different hospitals having different way to represent data.
Mm-hmm.
So and I assume that given that you want to forward the model, you are expecting that the model is talking about the same variables. Otherwise, you will have a clash when you're trying to do the average. So then are you assuming that the data integration happens before the model learning then?
Yeah, so very, very good question. And indeed, for this view, we assume that data is of the same form. And even more so in the vanilla version, we assume that it is IID. So really from the same distribution, which rarely ever holds in practice. And especially the hospital case is very good because there you not only have different distributions, but as you said, data is in different formats. Maybe was from a different machine. One MRI has a different resolution than another, and so on and so on. So here we assume this has all been pre-processed so that we can apply the same modeling. Now, dealing with exactly these problems is currently one of the big research directions that we face. I will say a little bit about this, but if you're interested, we can, and there's a little bit of time, we can discuss more in the very end, because it's indeed one of the very important problems.
Okay, thank you very much.
Okay. So, as I said, averaging is a key technique that most people use. There are a few other aggregation operators. I will present at least one. In general, you can think of any aggregation operator that you want, and it's a huge open research direction. The disappointing thing is that often enough, averaging works so well that it's not worthwhile taking something else. For researchers, this is really disappointing. From a practical perspective, it's actually very good. Let me just give you a quick example. So here you have 2D data points, and we have linear models. So linear model here is just a vector, in this case, I guess, without an intercept, so two-dimensional vector. We do classification, so the side of the hyperplane the point lies on determines how it is classified. We have our data set, and now we do a round of training, so all models locally adapt so that they classify their points correctly. We do another round of training with a few more data points, and now we want to aggregate them. We do that by averaging, so we share these models, and then we set them to the same average model. And here in this example, this all works out. All the models now classify all data points well. This is roughly how model averaging works. Now, the second big question is, when do you aggregate? And there are a few possibilities. There are actually like countless possibilities, but the big ones I want to discuss today is you can do it once at the end. So you have all your local clients, you run your learning algorithm till convergence, till you're very happy with the local model. You aggregate them once using averaging, for example, and then you're happy and go out and say, this is my model. This usually does not work very well. So what people rather do is they average multiple times during the training process, especially with neural networks, because there you have an iterative training process. So every epoch or every 20 mini batches, you average your models. And then the seminal paper that coined the term federated learning actually said, well, we want to save communication. So we do exactly that, but only with a random subset of the clients. And then there's also the idea to dynamically communicate, so only when the data deems it necessary. And I will present those a little later. Before, I want to say what makes federated learning efficient. So what are the criteria with which we decide whether an algorithm or an approach is good or is efficient? And the four topics people usually talk about are model quality. And this is a bit surprising for people that work in old school distributed computing or parallelization, because there you take an algorithm, you look at it very careful, see which parts are independent, code it in parallel, and then you run it. And the result you get is exactly the same as your centralized algorithm. A parallel sorting algorithm will still sort your list, right? In federated learning, this is not the case. If we average our models, we get something, hopefully something good. The best we can hope usually is that we are as good or close to as good as our centralized training, but we cannot guarantee it in all cases. So instead, we have to hope to get as good as possible and maybe be able to give some theoretical guarantees on how good we get. So model quality is a huge concern. Also, you have to keep in mind that in most scenarios, centralizing all data is just impossible. So you don't have to be as good as centralizing all data because nobody can do it in practice, but you have to be better than any practical solution. So if, let's say, you could centralize the data of 10% of your mobile phones, then you just need to be a good deal better than that. And you already make a benefit. The second big criterion is communication. So the motivation for federated learning was communication. By now it has shifted a bit to privacy, but communication was key. How can you reduce the number of bits you have to transmit? The next criterion is a bit under the rug in classical federated learning. This is the speed up. It's very important in classical parallelization. How much faster do you get when you add more machines? In federated learning, people usually say, yeah, speed up is nice, but we have problems that we just cannot solve in any way. So if we can solve them, it's already good. How quick it is not paramount. Or think, for example, in the medical setup, you have hospitals. They don't care if they have to run their algorithm a day longer. Nonetheless, speed up is an important topic, and it makes sense to discuss it a bit, also because on a theoretical level, you can see a little bit where the problems of federated learning lie. And I will discuss that in a minute. And the last very big chunk is privacy. I already said, data does not leave your device. That's great. Nonetheless, you send model parameters. And of course, you can try to infer from these model parameters something about the data. And you might have heard, it's actually possible to infer quite a lot. So how can you protect against it? And what does it mean for federated learning? These are, I think, the four big criteria. And I will now go through each of them and give you a little bit of a rundown of what results are there and give you a little bit of an intuition what you can do. So let's start with model quality. The first approach that was basically model averaging and a version of federated learning, if you want, to the best of my knowledge, was by McDonald et al. In 2009. And they trained EM models locally until convergence, and at the end averaged the local models. And they showed that this was as good as distributed gradient descent, which was back then the state of the art in distributed machine learning. But it is only good in certain cases. And in general, it doesn't really work. The reason is in deep learning, you usually converge to very different local minima. And then if you think of it as a mountainous region with valleys and mountains, if you are in two different valleys, then if you average, you end up on the mountain in between. And this is something you want to avoid. Also, it was shown by Shami and Srebro in 2014 already that averaging at the end in general can be arbitrarily bad. So there you can give no guarantee that it will be good, because a big problem that you have is with averaging, a single outlier can ruin your day. One bad data set, one bad model that lies far away from your good models, and it will drag the average away and your whole training basically fails. The usual way of doing federated learning is by periodic averaging. And here I just show you a simple toy experiment where I think it's 512 clients learn some noisy simple data distribution. And this type of plot is a cumulative error plot. So over the rounds, or call it time, you see how much error they accumulate. As soon as you have a horizontal line, you know that you have perfectly converged. And at the end, you see the higher you hit the 1,000 mark, the worse your overall error is. And I show you two baselines. One is serial or centralized learning. So you just collect all the data, run serialized training algorithm that converges very, very fast, as to be expected. And you have a system that does not synchronize at all. So you just have the average, or in this case, the cumulative error over all clients. This is, of course, a lot higher and did not even converge after 1,000 rounds. Now, this periodic averaging does very well, right? It converges quickly. It only achieves a little higher cumulative error than centralized learning. And this is what we often see in practice. It works surprisingly well. You never get as good as centralized learning, but you get good. One issue here is that once your model basically has converged, and here it's roughly at around 200, 250, you still communicate every 16 rounds. And this is, of course, not very efficient. Plus, in this case, I think the clients communicate every 16 rounds. That's quite a bit of bits you send around. So what, before I go to the next approach, let's just briefly talk a bit about model quality, because that's our topic here. You can show that this periodic averaging, if you average after each update step, is equivalent to centralized learning. So it is as good, with a tiny, tiny drawback that you have a different learning rate and a different mini batch size. And the reason is, if you do all these mini batch updates and then average them, it is as if you did one step with all the data combined. So instead of having B mini batch size, you have M times B huge batch. And because you average, you don't go M times along a long path, but you rather go M times in different directions and then average. So it is the same thing as if you walk this path, but with a step size that is M times smaller. This is a detail about federated learning that is often a bit overlooked, because this reduced learning rate and this increased batch size can in practice often ruin your day. That's not an issue if you have 5 clients or 10, but imagine you have 1 million clients. Let's say you usually have a learning rate in you do CIFAR with a neural network, you have a learning rate of 0.01. And now you do federated learning with these parameters on federated learning with 1 million clients. Then your effective learning rate is 0.01 divided by 1 million. And your mini batch size is whatever local mini batch size you have times 1 million. And we know from deep learning that very large batches usually do not converge to very good models. That's not always the case, and there's some debate about it, but usually large batches converge to bad local minima. So these issues can be a problem, and you have to keep them in mind. And actually, on the theoretic side, when we talk about speed up, this is exactly the issue that prevents you from having the holy grail of parallelization. Nonetheless, if you communicate every round, it is optimal. There are also some results on what happens when you don't, but this is rather rare. Before that, I want to go to the most, seminal paper that termed the coin federated averaging. It was by Brandon McMahon and his colleagues from Google in 2017, where they did periodic averaging, but they did 2 things. The first one is they really scaled it up. Actually, 3 things. They did it for a lot of deep learning methods, including convolutional neural networks and LSTMs, which has not been done before, I think. And in order to reduce communication with such a huge number of clients, they said, let's communicate with a random subset. And if we always pick, let's say, 10% of clients in each communication round, then after some time, the average will have somehow made its way to everyone, and it will be good. And for a setup where you have mobile phones, which is exactly the Google setup, this makes perfect sense. Because if you want to communicate, most people have their phone charging, they can easily send. Many people will have their phone with low battery, you don't want to send it. Some have used their phone and you have model updates, some don't. So it makes perfect sense to sample clients. And what they could show is that this is as good, or in some cases even outperforms, classical periodic averaging. So this was a huge result. The only thing that is not so nice is in terms of communication, they reduce it by a constant factor, but they still communicate already when they basically have converged. So it is not ideal in the sense of communication. When it comes to model quality, what you usually find in papers in the theory section is not a bound on how good is my model, but rather a convergence result. How quickly do you converge to a minimum? And for example, for strongly convex objectives, you can show that federated learning is as good as centralized learning in big O notation. So it has a convergence rate of 1/t, where t is the number of rounds, which is great. Plus, if you have a convex objective with the right model classes, you usually can say something about how good it is. These are the classical learning theoretic results. For non-convex problems, especially deep learning, you get a result that says you converge with 1/√, in this case, mt. So number of tries times number of rounds. This is a very good result, but it only says you converge to some minimum. The result usually says your gradient vanishes, it goes to 0. Yes.
So one question about convergence, like in practical applications, how do you think, so, supposing I have a collection of mobile phones that's generating data every day, and, after 10 days, I kind of converge. What role is there for federated learning to do after that? Like, do we periodically reset the model and learn a new model, or in practice, how does this work? Because
these convergent results, so a friend of mine called it learning theory mumbo jumbo, because the practical impact of these results is usually low. And I know I anger a lot of my peers right now, but I'm a huge fan of learning theory. The thing we want to deal with rather is, does it in principle converge? How fast does it in principle converge? And which assumptions do we need to make so that it converges? And then we can see which of these assumptions are violated in practice. So for example, this assumes that your task remains exactly the same throughout your learning process, which is in practice usually not the case. So what you rather have is an online learning scenario with distribution shift. That is a classical thing. So you learn, you converge to some result, but then the world changes and you have to adapt. This is not caught by these convergence results. Nonetheless, it's very interesting to study them to get an idea of what we need to assume. So do we need to assume that the learning is done on data that is purely IID? No, you don't. Actually, you can assume a little bit of difference in local data sets. How much can we? And so on and so on.
But in practice, what do people do? I mean, is federated learning applied more in an online setting or in a one-shot setting?
Very good question. So I have seen people using it in online settings. And I think that is how Google was using it. So the one big application they had was for their ad prediction in their keyboard. That is an online setting. So there you have changing models. But I'm fairly sure, so the Google approach usually is you have a principled algorithm that works well, and then you have lots of tricks and tweaks to it that make it even better. So I'm not sure how they do, for example, drift detection, whether they just let it happen or whether they have something intelligent there. My guess is they have something intelligent.
Okay, but usually when people write papers on federated learning, it's in some sort of a implied one-shot setting where you just say that this is the amount of data we have. And
yes, and when you think about, for example, the medical setup, this makes sense. You have a set of patient data sets locally. They won't change much because getting another label means a doctor going to an MRI scan and saying this is a cancer. This happens maybe 10 times a day. So it's not such.
It grows slowly. Yeah. Okay. Thank you.
Yeah, you're welcome. Okay. Nonetheless, these convergence results are interesting. There are actually quite a lot by now. But the big issue I have, especially for non-convex problems, is convergence does not guarantee you good model quality. You can converge very quickly to a very bad minimum that doesn't give you anything. So what we instead would need to look at is model quality. And the typical way learning theory gives you guarantees is they tell you something about the generalization gap. So you have a true error. This is usually the expected error you make on an unseen data point. And you have the training or empirical error. That is the error you make on your training set. And the generalization gap is the difference between the two. And yeah, usually you want that to be small. A small generalization gap, by the way, doesn't mean you have a good model. It only means that whatever training error you have is a good estimate for your true error. If that training error is bad, you still have a shitty model. So you need two things. You need low training error and a low generalization gap. Luckily, with neural networks, they usually can reach very, very low training error or even zero training error on most data sets. So that makes it very well. I stole this picture from a different talk about the double descent problem. So the interesting thing is that with neural networks, they are so complex that they can always or nearly always can reach zero training error. And then the question is, how can you then still bound the generalization gap? But that's maybe a topic for some other day. Now let's get to bounds you can make on this generalization gap. There's actually very, very little work on that currently that I'm aware of in the federated learning context. The one work I know is by someone I worked with, Jiajia Li. She worked on a neural tangent kernel interpretation of federated learning. Now, the neural tangent kernel is one way of how we can try to understand the learning dynamics of deep learning. And what you assume is that you are in what they call the lazy regime. So your weights don't change much during training. And it seems to be the case that how you initialize your network determines whether you are in this regime. And they usually assume that you have an infinite width neural network, which is a little bit impractical, but they also have results on finite width, and it works in practice. So this neural tangent kernel is defined as matrix H infinity. It's basically a Gram matrix over your data, but it has this random component. At least that's one way to look at it. And if you have this neural tangent kernel, then you can actually give a bound on not only the generalization gap, but actually the true error, the generalization error. And it looks a little bit like that. So the true error or generalization error is bounded by something that depends. How does it work now? It works. That depends on this neural tangent kernel and some term where the data set size plays a role. So n is in this case the size of all local data sets combined, and delta is a probability with which this bound holds. By the way, this is a very classical way of presenting generalization bounds. It's a pack-like bound, probably approximately correct. So the typical form that you have is the probability that your model is worse than epsilon is smaller than delta, or the probability that your model is good, so the error is smaller than epsilon, is larger than 1 minus delta. So delta basically says how confident you are in your bound, and epsilon tells you how good your model should be. All right. There's, once again, this field is evolving fairly quickly. I'm not aware of any other current federated learning generalization bound, and I might be wrong here. There's one other that works by using a different aggregation operator, and I promised I'd show you at least one, and I picked the most obscure one you can find, well, because I made a paper about it, and this is the Radon point. The Radon point is some geometrical point that was introduced by Johann Radon in 1921 to prove Haley's theorem, and how it's defined is a bit weird. So you have a set of points, in this case in 2D, you need at least 4 points. And what you can do then is you can partition your set of points into 2 sets so that their convex hulls intersect. What does it mean? Well, we have our 4 points here. Well, I'm really bad at targeting. These are our 4 points. And then we partition them into the orange points and into the purple points. And their convex hulls in this case are these lines, and they intersect in a single point. That's a Radon point. Now in 2D, there are only 3 possibilities of how points can roughly lie. This is the first one, there you have a single Radon point. It could also be that one of the 4 points is inside the convex hull of the other 3. That's the rightmost example. Then the Radon point is exactly that point within, because you basically pick the 3 outer ones as your one set and the inner one as the other. And the last possibility is that all points lie on a line. Then you have a whole line segment as an intersection, and every point on that line would be a Radon point. Now, I think the most important question is, why would anyone do that? Well, it's a fairly robust point in the center of a cloud of points. So if you have one point that is very, very far away, imagine, for example, that this F3 here is an outlier, and imagine it would lie down at that waste bin, the Radon point would remain the same. So it is fairly robust against few outliers. What can you do with it? Well, you can do federated learning. You need the right number of clients. So what Radon proved is, in order to construct such a Radon point, you need d plus too many points. That's the so-called Radon number. The d here refers to the dimension of your models in your case. So if you have linear models, it's equivalent to your data dimension, maybe +1 if you have an intercept. If you have a neural network, it's already different because it's the number of weights your neural network has. And now just imagine if you have 1 million weights, you need 1,000,000 and too many clients to compute one radon point. It makes it slightly impractical. Nonetheless, how you compute the radon point is, well, you don't have to actually construct these sets by hand, but you can write that down as a system of linear equations and then solve it in time cubic in R. So that is all good. So what we do is we have our R many clients, we train a local model, and then we can compute the radon point of those. And let's assume that we have a learning algorithm that gives us one of these old school epsilon delta guarantees. So we know on this small data set, we get some guarantee that our model is not worse than epsilon with a probability of 1 minus delta. And usually this delta will be very large. So we have a very low confidence because our data sets are small. Yes.
So when you do your neural tangent kernel, is D the number of local data points then? Because it's a kernel model that's non-parametric essentially.
Neural tangent? Well, I'm not in neural tangent kernel. I'm now at a different approach.
But could you use the neural tangent kernel to kind of go down in the number of parameters of your model?
Can you use? The neural tangent kernel has, I think, an implicit dimension equal to the number of data points you have, because it's a ground matrix.
Yeah.
So if you have 10 data points on, then the best you can have is you have 1 data point at each client, right?
Yeah.
So you can at best have 10 clients for 10 data points, but you need 10 plus too many clients because you need D plus too many to compute a radon point. So that really ruins your day. That's one reason why the radon machine doesn't work for vanilla kernel methods, including the neural tangent kernel, because the intrinsic dimension is usually equal to the number of data points, but you need then number of data points plus too many clients, which doesn't work. So
makes sense.
Good, very good question, but unfortunately, it doesn't help you. Okay, so just to recapitulate, we do just standard federated learning, but instead of the average, we compute this radon point, and we assume that for our local learners, we get some epsilon delta guarantee. Then that was radon number. And then you can prove that the probability that your model is bad is reduced quadratically. Yes. Let me just throw these up while you give a question. Just I haven't forgotten this, just to say. So this only works for convex loss functions. So it's the probability that the radon point is bad is smaller than the squared probability that your weak models are bad times R. Okay, now please.
How do we get the radon point if we have more than 2 dimensions?
So good question. In general, if you have an arbitrary number of dimensions and you have D plus too many models, Radon's theorem says that you can partition your points. So it basically means you have one convex hull of a set of points. So you have a set of weights alpha that you apply to some subset of points, and you have a set of weights beta that you assign to the other subset of points, and they should be equal because the convex hulls should intersect. This you can write down as a system of linear equations. Then there's no unique solution to it, but you can, for example, fix the first dimension to 1, and then you have a unique solution. So what you in the end do is you write everything in a nice matrix, run your off-the-mill NumPy solver on it, and get the radon point for arbitrary dimensions. All right, but yeah, it's an important question. The radon point is really not intuitive. Okay. Now, as I said, if you do this radon computation once, then the probability of having a bad model is reduced quadratically. But of course, you can stack that. So if you have a huge number of clients, R to the H, you can partition them into sets of R, compute a radon point of each. That gives you a model. A model is just another point. So you can then partition these R to the H minus 1 many points again into sets of R and compute the radon point, and do that until you are left with a single uber radon point. And for that one, you can then easily show by applying the previous equation that it reduces the probability of a model being bad doubly exponentially in the number of iterations that you run, or the height of that tree. Okay. So what that means in practice is, if you have an algorithm that gives you a learning theoretic guarantee, the radar machine tells you how good it will be if you apply it in parallel with that radar machine. And you can then easily compute these guarantees. All right. I will now go to the next big topic, which will be communication. I will have a few back references, but please, if you have any questions in the meantime, just go ahead. So we talked about periodic averaging, and the amount of communication you have there is very easily computable. It is number of rounds divided by how often you communicate times the size of your model. So it's an O of T divided by B. And for federated averaging, you reduce it quite a bit, however, only by a constant fraction. So reducing your overall communication by 10% is amazing, but still you cannot go lower than that. It's 10% of whatever communication you have. The question we had at some point is, can we do a little better? And the idea is that it would be best if we only invest communication when it's useful. So the trick we had, and I just want to divert a little bit into it, is that we say, if models are very, very close by, then averaging basically doesn't change much. So it's a rather useless communication. Whereas when they are very far away, then it might make sense to synchronize, to average them. So we only want to communicate when the divergence or the variance of models is larger than a user-given threshold. The big problem with that is, if I want to compute this equation up there, I need to communicate, which kind of is pointless, right? So we needed to have some local conditions that we can check so that we do not need to communicate. And the local conditions are, we take a reference point, usually the last known average, and we check whether the distance to this point is larger than our threshold. If it is not, we are guaranteed that everything is good. If a local condition is violated, then the global divergence threshold could be crossed, but we need to communicate to find out. So let's see how that works in practice. We have a system with 3 clients. They have their actual average in blue and this reference point, which is some older average, in purple. And now assume that one model has trained a lot and it has moved away. So not only is the true average now not inside our safe zone anymore, but also the distance to that reference point is crossed. So now we need to communicate. We set all points to the average. Now we can update our reference point and we're again in a stable configuration and don't need to communicate. Now, the good thing is we tried that out in practice in many projects, and we found that this indeed saves communication. So for any desired model quality that you want to have, you use less communication, or in other words, for the same amount of communication, you get a better model quality, depending on you set this threshold. And we compared it, of course, to federated averaging. And what we see is, with roughly the same model quality, we reduce communication by between 16 and 50%. And it, of course, depends on how hard your learning problem is, because we actually give a guarantee on that. So first of all, we guarantee that the loss is similar to periodic averaging, which is important, so it's not worse. And the communication is then linear in the number of clients and bounded in the hardness of the learning problem. So if you have a very easy learning problem, it's guaranteed to communicate very little. If you have a hard problem, it communicates more to achieve good model quality. And just for fun, we applied this in a project with Volkswagen to train autonomous driving functionalities. And what I can show you here is this toy experiment we did, where we had this driving simulator, and we had 5 cars that would drive around and learn locally and then communicate using this dynamic averaging. And what you see here is the model that in the end came out, and it drives around fairly okay. Okay. One project we did that was a lot of fun. Lucas is the first author here. So this was a great idea. The point was, what if we really want to save communication? So that's very relevant to today's summer school. What What can we do if we have not processors, but just an FPGA that only can do integer operations? And what we did as an idea was we took integer exponential family models that have been developed by Nico Piatkowski and did dynamic averaging for those using only integer operations. And the main trick here is that you can compute the average with just a bit of ANDs and XORs and bit shifts. And if you then take realistic numbers for the number for the amount of power you need to communicate, which is usually the most expensive thing you can do on an ultra low power device, and compare it to how much communication you save if you do this local training, then you see that you save that you save energy by a few orders of magnitude. That was a fun project. Now, let me go to this one topic that is a bit under the rug, which is speed up. So how is it defined? It usually is defined as what is the runtime of my centralized algorithm divided by the runtime of my parallel algorithm. If I have a speed up of 2, it means my parallel algorithm is 2 times as fast as my central algorithm. And usually this is measured in how many clients you invest. So typically the best speed up you can have is linear. If you have twice as many clients, the speed up is doubled. Okay. The big problem here is, I said that before, in federated learning, the model quality we get, or the model that we get, is not the same as in centralized learning. So what does speed up mean here? This was defined for algorithms that output the exact same thing. How much quicker can you sort a list? Here we get some model. So what we usually say is, well, we cannot get the same model as centralized learning, but what if we can get a model of the same quality, or at least that gets the same quality guarantees? And this is how speed up is then measured. So what's the runtime of the centralized algorithm to get a certain model quality or quality guarantee divided by the runtime of the parallelization. So big thing is we need to compare runtimes for achieving the same quality. Okay. As I said before, if we communicate every round with this periodic averaging, we know that it is the same as centralized learning. So we get optimal quality, right? Yeah, well, we have this problem with the mini batch size and the learning rate. So if our effective learning rate is eta divided by m, and our effective batch size, m times b, is indeed good for our learning problem, then we have perfect speed up, linear speed up, the best one can dream for. Twice as many clients, and it's twice as fast. This would be the holy grail of parallelization. It was called embarrassingly parallel at some point. The big problem is exactly in the learning rate. So for very large problems, this learning rate becomes very small and the batch size becomes very large. And this was first noticed by Shami and Srebro in 2014, where they showed that in theory, you can never, given any number of clients, get the optimal learning rate. It might work for a certain regime, like between 5 and 100 clients, but if you then want to scale up, at some point it breaks down. So they said, in principle, and in principle meaning in theory, given that you want to scale up arbitrarily, there is no speed up over centralized learning. And the main reason is that for very large numbers of learners, the learning actually deteriorates. And I had a bachelor student actually doing an experiment once where he trained local models with a certain learning rate and then looked at the central optimal learning rate, and you can see that it learns slower, the federated averaging. But if you increase local learning rates, it gets better and better. But if you increase it too much, at some point it breaks. Because then if you have a too large local learning rate, your model jumps wildly and you do not converge. So what does it mean? In theory, federated learning should not work. In practice, it does. One thing is that it seems to be that not communicating every round is actually good. So what you do in practical federated learning is you train for an epoch or at least half an epoch, and then you average. So this behaves differently than just centralized learning with a larger gradient. And it is not exactly understood what that means for the speed up. So this is a huge open problem. If you are interested, that's definitely a big research direction where I think not much is done yet. Let's get back to this radar machine, because that's one of the few approaches where speed up has been analyzed. And just to throw it here, it's not too important, but just to give you an idea on how you can compute it. So let's assume you have a learning algorithm that has a polynomial runtime, so something like m to the power of k. Then the radar machine has a runtime that is polylogarithmic in that. So it's log to the k of m plus another log m term. However, you need quasi-polynomially many clients, so you need m to the log r many clients. That's quite a bit. You remember the radar machine requires this huge amounts of clients so that you can build this tree nicely. Nonetheless, this is nearly optimal, and optimal means here in Nick's class, it's one of these classical runtime complexity classes that have been proposed for parallelization. Okay, and in practice, I mean, the speed up is nice. If you use 150 clients, you get a speed up of something around between, let's say, 50 and 200, so exactly what you want. All right. So speed up is, again, not the most important topic today, but let's go to one that is definitely at the heart of federated learning, and that is privacy. I started this lecture by saying you only send model parameters. That's great. Data never leaves your device. And that was a selling point. But people very quickly found out that you can learn a lot about your data from your model parameters. And here's an example. Actually, you learn from gradients, not model parameters here, but the picture was just so nice, so I took that one. So it's an original picture. You get the gradient from your model, not the picture, and you reconstruct it using only that gradient. And as you can see, you get quite good reconstructions. One's done with the ResNet 18 and one is with the ResNet 152. Yes, please. Sorry? So the gradient really means that you compute the gradient for this image and send it. So if you would do distributed gradient descent. Another option how you could get it, if you send model updates every step, then you just take the difference that gives you a gradient. Sometimes some federated learning algorithms or implementations actually send model updates instead of the whole model. And this is a way of getting this information. Just a second. In principle, you can infer about local data even just from the model parameters. So you can, there's the whole inversion attack where you can reconstruct or try to reconstruct the local data set. And even easier is the membership inference attack, where you take a data point and just ask, was that in the training set or not? And this is fairly doable. Okay, sorry.
Sorry, what do you mean from this is just the inversion attack that it is in the literature, kind of the inversion attack? Just it is that this kind of the attack or taking data from the gradients?
This is an inversion attack. So you take a gradient and try to reconstruct the original image that was used to create this gradient.
Okay, thank you.
Mm-hmm. So what can you do against such attacks? There is a whole set of classical solutions where I know very little about, which is classical cybersecurity methods. Save your channels, encrypt everything, be proper about your security. And these work. I mean, these are guaranteed to work. There are a few problems. One is if you have, for example, a curious server, then he gets the decrypted models to compute the average. That's a problem. He can actually look at the models. There are approaches that use homomorphic encryption that try to avoid it. I've heard mixed things about them. Some say it's the holy grail, some others doubt that they truly work. I'm not qualified to have an opinion here. The more standard approach that people use is they apply noise to the parameters, because if you add proper noise, you can guarantee epsilon or epsilon delta differential privacy. So this differential privacy is, I think, the state-of-the-art notion for a theoretical notion for privacy. And it basically says if I change a single element in my data set, how much does my function change? How much can I learn from that, right? So classical example, I have the average height of everyone in that room. If I throw a very large person out, the average goes down, then I can assume that this person was larger than the average. If I instead add a bit of noise on my results, so you always don't get the correct average height, but only a noisy average, then I don't know, was the increase because of noise or because the person was indeed larger than the average. This notion is, I think, the best we can do currently from a theoretical perspective. And this method of adding noise is easy, right? Just take the model, add a bit of noise, maybe clip your model updates. That's super easy to implement. You lose a little bit of model quality because you add noise, but you gain privacy. Still, by the way, this is an example for that. So you have some private data, you add a little bit of noise and then try to reconstruct. If you have very little noise, you can still reconstruct very well. If you add a bit more noise, then it's impossible to reconstruct. So this works in practice. There are some doubts whether differential privacy is indeed the best weapon of choice. I've recently had a nice conversation where an expert told me the actual noise that you would have to add to get a proper guarantee is so large that it really ruins your day. Or in other words, if you add normal noise that still leads to proper training, the guarantee that you get, if you really compute it down to the core, is basically useless. I cannot confirm that. I can only say that these are doubts that people have. No, there's a question in the chat. What reason is there not to use homomorphic encryption? I don't think I'm really qualified to answer this question. I have a few ideas and I will just blurt them out, but please take them with more than a pinch of salt. One reason is apparently it uses a huge overhead in computing and communication because you need to send all this additional data so that the coordinator can actually compute the average on the encrypted models. That might be a problem in many scenarios. In healthcare, it would not be a game changer because we are in what they usually call cross-silo scenarios where we don't care about communication and computation resources because we have them. There was one opinion I heard, and I again cannot confirm that homomorphic encryption is designed as a two-party protocol. So I can communicate with one party, it can perform a computation on the encrypted version and then send it back. So in order to do it on multiple parties, you would have to share decryption keys with these parties, which would open several vulnerabilities. But again, this is not my expertise, so be careful with that. All right. It seems that differential privacy has a few more problems than just as practical. And one is that it by design hides small subpopulations. That is what it should do, and this is actually a good thing about it. But in some applications, and especially in healthcare, small subpopulations are really important. And especially like think of a rare disease. It's a very, very small subpopulation of your data. So if you hide their impact, you will not be able to learn a model that somehow does something with this rare disease. Plus, it really requires lots of noise if you have very small data sets, because then one small change actually has a huge impact. So it is not the right tool to analyze small data sets. Nonetheless, it is the current state of the art. And I guess the right way to look at it is it's a bad tool, but it's the best we have. All right. There's one other idea on how to improve on that, which is to share predictions instead of model parameters in kind of like a co-training approach. It was called distributed distillation. It was published at NeurIPS in 2021. And the idea is you have a global unlabeled reference data set. And instead of sharing model parameters, you share predictions on that unlabeled data set. The unlabeled data set is public, so nobody cares. And you just send the predictions. Here's, that's from the paper. you have a neural network and it trains both on your actual training data, your little pointer, on your training data, and it also wants to agree with the other clients on the unlabeled data. That's roughly the training objective. And then this gives you a new custom loss function that you can use in model training. And it actually, the experiments look good, so it seems to work very nicely. The only problem is there is no formal privacy guarantee yet, so it's a bit unclear what guarantees you get. But then again, this is current research, so maybe the moment I say it, there already is something new. Okay. This would conclude the big chunk of my presentation about these 4 points. I will now divert into some trivia, some advanced algorithms, some problems we haven't seen yet. So if you have questions, now would be a good time to do like kind of a wrap up and then go to the more advanced topics. Good. So either I'm very good at explaining or bored you to death. Let's go on. There is a bit of a confusion about the name. So what is federated learning? What does it actually mean? What about parallel, distributed, decentralized, whatever learning? And I don't have a good answer. Federated learning was proposed in 2017 as a name. And the idea why it's federated is you have a federation of clients and they have a single server or coordinator that somehow manages that federation. Nonetheless, I mean, even before people realized you could do that in a hierarchical network and other network topologies. So not sure how important it is that it's a federation. Distributed learning and model averaging was, as I said before, already done by McDonald et al. In 2009, so it's definitely older. We did periodic and dynamic averaging for online learning already in 2013. That was Mario Bolai's work. And the whole decentralized learning, where you really do only peer-to-peer communication, that was done a lot earlier. So there's peer-to-peer averaging using gossip algorithms. So I think the work of Mark Gelasity since 2005 is a good start here. So the techniques of model averaging and so on are not definitely started with in 2017, but basically there's a huge set of works from the 2000s till now. And by now, the term federated learning is the one that has stuck. In my PhD, I called it black box parallelization because it treats the underlying algorithm as a black box and doesn't care, it just parallelizes it. I thought that was very smart, but it kind of didn't stick, so you can directly forget about it. The second big question is, what about sharing gradients? Is that federated learning? What I mean is, what if you compute gradients locally, and instead of then doing an update step, you share the gradients with some server, you aggregate these gradients, take the average, and by the law of total gradients, that's actually the correct gradient of the entire batch, and then you do one update at the server. So that's sometimes called FedSGD. This has been around for quite a while. There's a seminal paper by Overdeckel. It's optimal distributed online learning using mini batches from also 2009, where it has been properly analyzed. And once again, it's correct in the sense of it's a proper parallelization. You really get the right gradient descent, only with a different batch size. That's the only difference, because you now have the gradient over all your local mini batches. But other than that, it works. The reason why it is not used in practice, I think, is that it's designed for systems that have a very tight network connection, because you have to communicate for every update step you make. You need to compute the gradients, centralize them, then make one update step, compute gradients again, centralize, do one update step. This is often impractical. It works well if you are working in a cloud, in a cluster, in a very strongly connected system, but it does not work with mobile phones. So that is one reason why federated learning is more successful. There's another reason that for deep learning, these big batch sizes seem to be a problem. So apparently neural networks generalize better when you have a lot of stochasticity in the training process. That comes from learning with a small mini batch. So if you do this fed SGD or distributed gradient descent, then your batch size quickly becomes so large that it is nearly a normal gradient descent, which converges very quickly to the nearest minimum. But for neural networks, it seems to be not so good. Nonetheless, this is a great algorithm, right? So if you are in a tightly connected system, or if you have, let's say, a convex learning problem where you know you just want to go to that minimum, this is really a very, very good approach. Now, slowly coming to the end of the lecture, and I want to use that time to go into a few more advanced problems. And the thing is, the field has evolved quite a bit in the last years, and it is so big now that I cannot even try to cover all the problems. I'll just take a few very prominent ones and go a little bit in that direction. The first, and I think biggest one right now, is what about non-IID data? So in the classical analysis of federated learning, we assume all clients have data drawn IID from the same underlying distribution. We run the same learning algorithm for the same model type, and then everything works nicely. In practice, that rarely holds, and we know that. The medical example is very good. We have X-ray machines that all have different saturations. One is dim, one is not so dim, different resolutions, and so on. The same is for autonomous driving. Every manufacturer, and even every model, uses a different camera, a different LiDAR system that can really ruin your day. You might be able to pre-process a bit, but you cannot get rid of it entirely. It's also a big problem in the medical domain where you have hospitals that just see different patients, right? Maybe the ratio of men to women is different. Maybe the ratio of people with a certain disease is different. Maybe the reason with ethnicity is very different. And this can have big impact on the model. So we know from the US, there's the chronic kidney disease, which is a huge health epidemic, not only in the US, but also here, but they're slowly trying to cope with it. And a chronic kidney disease is a disease when you detect it very early, you just take a few medications and you're good. You have a perfect life, everything is nice. If you detect it very late, you die. So there are, I think, 5 stages, really not an expert, but you want to detect it very early. And you can easily detect it. It's a very simple test, blood test that you can do, and you're happy. But you don't administer a blood test just like that. So you only do it if someone has symptoms that lead towards it. And what people found is that, for example, these blood tests are administered more often for white people than for black people. Now, this is not pure nastiness, but it is because the analysis that is done is usually done on data sets where black people are underrepresented. So the analysis overfits on white people. And this is a fairness issue that we know from many other examples in machine learning. But these non-IID problems are very, very important in practice, and we're slowly starting to approach them, more slowly actually for a few years now, but nonetheless. Now, there are different ways of how your data can be distributed differently. The 2 classical ones is your label is distributed differently, or your features are distributed differently, or any combination thereof. Different label distribution means, for example, one hospital has more sick people of a certain disease than the other. Different feature distribution means one has more healthy people than the other, or in the car, a different camera than the other. In cars, you also have the problem that one drives in a rural area, one drives in a city. The driving behavior is hugely different. The images they see are hugely different, and still you want to somehow deal with that. There are a bunch of methods developed specifically to tackle these problems. There's FedProx, which and FedAdam and Scaffold. They tinker with the learning algorithm in such a way that it is more robust to that. So FedProx does a proximal gradient descent, not a standard gradient descent. And this makes them very robust to non-IID local data. You can even show that if your data is not too different, then you will guarantee convergence. That's very nice. There is, for heterogeneous feature distributions, there are 2 approaches, Moon and FedBN. In FedBN, you use the batch normalization of neural networks to homogenize local data sets. And that also is simple, but works very, very well. Now, at the very extreme end of that, before in non-ID, we assumed that we want to still learn one single global model just from very different data sources. But why would you want that actually? I mean, why not have models that are in principle solving the same tasks, but are fine-tuned or specialized on the local data distribution, right? Why would you want a subpar global model in your hospital when you can rather have one that is really, really good for the people that come to your hospital? Or in another way, why don't you have a model that is very good at driving in rural areas and one that is very good in driving in cities? And then you might switch them, whatever. I mean, you can imagine all kind of engineering tricks. And this is a very, well, not very new, but it's still quite new branch of federated learning. Very sorry. Thank you. And it's called personalized federated learning. And the idea is you have local models that are specialized on local data, but still they learn from others and try to collaboratively solve the same problem. And this has huge relations to multitask learning and transfer learning. And the borders between those are very, very gray. Of course, problems may not be too dissimilar. If they are very dissimilar, then you cannot transfer any information. And one example I want to give of what you could do, because there are millions of approaches, but this one I find very nice, is that they assume you have a set of base distributions, components they call it, and every local data distribution is a mixture of those. So assume that one distribution says how a certain disease acts in females, one in males, one in Hispanics, one in whites, one in blacks, and so on. And your local distribution is always a mixture of those. And what they can do is they can learn two things simultaneously. They learn these base distributions and the local mixtures. And that's quite impressive. And they then show that they reach good accuracy independent of how many clients participate and how many mixture components you have. This was a nice and theoretically sound approach to that. But there are many, many others. And a very simple approach is just do some local fine-tuning after training. And from this very simple approach to this, there's basically every possibility of tricks you can use. And that is now a hugely popular topic. There was a question? Did you have a question? Sorry. Okay. Oh, good. All right. Good. One other problem is what do you do when you have small data sets? So that's the recent work my group is doing. So let's assume you only have 2, 3, 4 data points. With deep learning, that is very bad because the model you get from that is so far from anything sensible that averaging these models doesn't lead to anything. What you could do is what we call daisy chaining. So you take a model, send it from one client to the next, learn there a bit, to the next, learn there a bit, and then to the next. And with each hop, you get a larger effective data set. And if you had like 10 hops with 8 data points each, you have effectively trained on 80 data points. And if you combine this daisy chaining with averaging, sending all these models around wildly, training on all the clients, and then averaging from time to time, you can actually train. And of course, you have a lot of privacy concerns there, but I don't want to go into the details. The nice thing is that with this technique, you can train, in this case, a simple neural network on a synthetic data set with only 2 samples per client. Or we did it here on for linear models on the SUSY data set, also with only 2 models, two data points per client. And of course, if you want differential privacy, I told you 5 minutes ago how bad differential privacy is. We did differential privacy. What you usually then want to show is that if you add noise, reasonable noise, then your model quality doesn't deteriorate a lot. And actually this hopping with local training is really robust against noise. So that works quite well. Okay. With this, I want to summarize. So I hope I gave you a good intuition of what federated learning is, which directions you can branch out, what are interesting current topics, what does it mean to be efficient for a federated learning approach. So the main idea is always that we want to collaboratively train a model. and that averaging works surprisingly and disappointingly well. We usually assume that data is IID. We use the same training algorithm. We use the same model type or model architecture, but there are many current approaches that try to get rid of these assumptions. There are a lot of results that prove convergence, but there are few that prove good model quality. This approach is communication efficient in the sense that you save a lot of communication, and by client subsampling, you can really get very, very low, or you can use dynamic averaging, of course. It has a high speed up in principle, but you have this theoretical problem with the learning rate that often ruins your day. And in the same way, it preserves privacy in principle, but you need some additional protection to really make it private. For example, using encryption or using noise on your models. All right. Lastly, because I have 5 more minutes, I want to use that to just advertise my group. So I started it fairly recently. It's a research group that is at the Institute for AI in Healthcare, and it's basically at the junction between university clinic. We work with real doctors and real patient data, and at the same time, it's at the Ruhr University Bochum. So we combine basic research and practice in healthcare. So when you're interested, please, we're always looking for talented people. That was the advertisement block. I will put these slides up, so there's a bunch of references you can go through. And with that, I'm at the end of this lecture. Thank you all for your attention. Thank you for the great questions. If you have any more questions, I think we have a few more minutes, and I'll try to answer.
Yeah, thank you very much for this very nice lecture. Yeah, are there any more questions?
Thank you. Great talk. Outside of the Google keyboard example, do you know of any other sort of important or large examples where federated learning is used in practice?
I know of many companies that play with it. There is a federated learning is implemented in the so-called Raccoon network, which is a network of all radiologies in Germany. So all radiology clinics are networked there, and you can do federated learning in this network. I know that several car manufacturers are highly interested and play with it. I am not sure about whether it is in production. And from a personal experience, one big problem is if you have a new machine learning task, it's already very difficult to solve it in general. Now, federated learning usually adds a complexity to it that makes it very, very nasty. So that's why I try to only parallelize things where I know somebody else solved it in the centralized case, because then I have a chance. Doing the whole pipeline is in practice very difficult. And I think that especially companies need to still build up the know-how on how to do that effectively. Plus, there are not too many companies where this is really a need. In healthcare, there's a real need. In mobile phones, there's a real need. And maybe in autonomous driving, but I'm not sure. So it's still a big question of whether it's better to do federated learning or just do GDPR conform encryption and anonymization, because often that's where companies have competence and know how to do it.
Any more questions? Is there a question in the chat? No. Okay. If there are no more questions, thank you again.
Thank you very much.